All right. So all our best efforts thwarted. No Friday move. But then I was like, well, we're heading into so that kind of that threw me off mostly, I think, and I feel really bad for all the back and forth and all that, all for nothing. So I apologize for that. But this Friday, I'll make a video and you can watch it on your own time so that we don't have to meet here on Friday before the long weekend, because I'm gonna go ahead and say it would just be me here probably, and that's not fun. That's kind of annoying for me personally. And so video I don't want to say instead of lecture, it's just going to be me sitting down saying the same stuff. So how about video lecture will be posted on Moodle for Friday this week. It kind of works out well because I've also got test number 1 will be on, October 21st, which is a Monday, of course. I was laying out all the days and I had accidentally scheduled a test on a Friday because I wasn't really paying attention, and that's not cool. But can someone confirm that October 21st is, how about that someone is me? It is a Monday. Okay, that's good. And it works out well because then the Friday before we will have a meeting here. I'll do some review and just kind of tackle some questions and that kind of thing. So, but as always, I'll post the recording afterwards. So, okay. Any questions before we begin? No? I'll post, or I'll write review in class on Friday, October 18th. In case that wasn't clear. Hey, it's open, nice. Whew. All right. Logic. But first, I'll check in again. Any other questions? There hasn't been one. No. Okay. Logic. Lots of fields use logic, obviously. Law. There's a lot of logic in law. Computer science, a ton of logic, sadly for us. And I don't know, philosophers use a ton of logic. We're just gonna kind of touch in on it, introduce some of the main concepts. We're really gonna lean on what's called a truth table, and they're actually really fun to do. And so so we'll be working a lot with truth tables and just introducing some of these core logic concepts. And so where do we start? First thing we need to establish is, what is a proposition? A proposition is a statement, okay? A statement that can either be true or false. Hence, where we're heading is a truth table with all the different options of true, false for a proposition or one or more propositions. Okay? So it's really important that we know what a proposition is. And you just don't call it a proposition, right? And so a proposition is a sentence in which one and only one of the terms true or false can be meaningfully applied. So for example, 4 is even, It's either true or false, right? And so 4 is in the set of 1, 3, 5. It's either true or false, right? So these are just statements. Okay, and I want to follow it up here with they're really just statements. Right. So a proposition is a statement. Right. And then we'll have logical propositions, so logical statements. Okay. And so there's lots of different ways that we can combine simple statements, so simple propositions, into compound ones or kind of bigger statements. Okay. So we use things like and, or, not, if then, and if and only if. Right? So all of those are kind of logical connectives. Yeah? And so we can link up more than one proposition to make a bigger statement, and that's what logic is. Okay? We've seen these before, and, or, not, right? We looked at sets, right? And is where they're both true at the same time, or is where one or both are true, right? And then we looked at the negation, the not, which was the complement of a set. So we've seen these before, just in a different context. So if we have two propositions, I just kind of pre-read the sentence and it's kind of worded in a weird way. So since each proposition has two possible truth values, I want to read it from behind. So there are 4 ways that truth can be assigned to two propositions. So if we have two propositions, usually we denote propositions with a lowercase p and a lowercase q. Our st is kind of where we build our default propositions from. And so if we have propositions such as P and Q, P has 2 possible truth values, right? True or false. Q has 2 possible truth values. And so overall, we're going to have 4 different combinations, right, of truth values for this this joined proposition. Okay. And so first thing we're going to talk about is the word and. Okay. Now, and is called a conjunction or a logical conjunction. Okay. So from sets, right, we know that, okay, and is really only true if both of them are true at the same time. Right? And so if we have propositions P and Q like this, I'll zoom in. A proposition P and a proposition Q, then we denote it P and Q with this kind of point here. We're used to that upside down U, right? But here, this is and, a logical and, okay, or a logical conjunction. It looks the same, it's just pointy, right? And so let's talk about this section of the truth table for a bit, just these guys here. Right? P has 2 possible truth values, right? It's either true or false, and Q is either true or false. But we want to highlight, or what's highlighted is all the possible combinations of true false that we could have, right? And so this is all the possible combinations of P. I'm being careful to not write P and Q because that means something, right? I'll just write P comma Q. As we've seen here, P and Q means something else. So what we do is we start with P at 0, 0, 1, 1. Okay? And then we alternate 0, 1, 0, 1. And that'll make sure that we have all our possible combinations for PQ. Okay? So each line, and I am going through these notes, but I'll just talk about them. Each line represents a case, right? 0, if we let 0 be false and 1 be true, that's pretty common, right? And so here, let 0 be false and 1 be true, or represent true. If P is false, Q is false, then P and Q is also false. Right? If P is false and Q is true, then P and Q is false, right? Because they both have to be true in order to be true. If P is true and Q is false, well, P and Q again is going to be false. The only time that the conjunction, so the and, is true is if P and Q are true, right? 1, 1. Yeah, they both have to be true in order for the overall and statement to be true. Yeah, so they both have to do it. Hence the and. Also notice that these, if we read these as binary, right? In binary, in binary 0, 0, 0, 1, 1, 0, 1, 1. That's 0, 1, 2, 3. So they're in order, right? 0, 1, 2, 3 in binary. So they're in order. And that's the order that we're going to use. Wake up time. Where is it? Where is it? I think I have it maybe a little bit later. Why isn't it on here? How do we know how many lines we need? That depends on how many propositions we have that we're dealing with and working with, right? Because we need to look at all the possible combinations. Uh-oh, that sounds familiar from a long time ago now, right? But if we have n propositions that we're dealing with, we're going to need 2 to the power of n rows in order to outline what all the possible combinations are. Okay? And so I am shocked really that I don't have it in here because I know I meant to. Here, I'll do it in red. I'll punish myself. For n propositions, there are 2 to the power of n possible combinations. Therefore, would need 2 to the power of n rows. We can check. Here I'm just dealing with P, Q, so I have 2, so n is 2. 2 to the power of 2 rows covers all my possible combinations. All right. If I introduce a third proposition, which we'll see, right, then how many do I need? How many rows am I going to need? I'm going to need 2 to the power of 3, so 8 rows, right? And what you're going to do is you're just always going to start with half of them as zeros for P and half of them as ones for P, and then start kind of cutting those in half. We'll see an example, or we'll see lots of examples actually. Okay. But as you move through the propositions, you just kind of cut them in half. So you don't need to think about binary really, but it is there lurking in the background, and it gives us some natural order. Any questions so far? Okay, how about the logical disjunction? The conjunction, I think, is relatively, I can kind of get there from the word conjunction, but with the and, right? You want to be able to link these two words to what they're actually doing, right? The disjunction, I have a harder time with. That's just a matter of memorizing for me. But the disjunction is the or. We're used to seeing the or as a big U, right? But now the or is going to be a V, but it's the same essentially. So if P and Q are propositions, their disjunction P or Q is defined by this truth table. So notice how we've set up just the basic P and Q lines, or rows, or columns rather, 0, 0, 1, 1, 0, 1, 0, 1, and then we've covered all the possible combinations of P and Q. P or Q, now only one of these has to be a 1 for it to turn into a 1, right? So 0 or 0 is 0, right? 0 or 1 is 1. 1 or 0 is 1. 1 or 1 is 1. Huh? And if you prefer to read them as true, false, you can, right? False and false is false. False and true, or sorry, false or true is true. So you've got just one true in there. Huh? Yeah. So those you'll need to be really fluent with, right? The ands and the ors. We'll need to be fluent with all these, but definitely the ands and the ors. But I also think that they're relatively straightforward. How about the negation? The negation can be done on just one proposition P. So if P is a proposition, so if P is a statement, then it's negation, not P, which we've seen with the complement of a set, right? We are going to denote it by this little guy here. That's not P. Although I will make a note that on your assignment, or it could be tilde P, just because getting that not, the logical not, is kind of annoying in our homework system. That's the only reason. And so we're going to use a tilde P in mom assignments. Oops. So just be aware that they could be used interchangeably. But in these notes and in the textbook, we use the logical not operator. The negation just flips the truth value, right? So if P is false, not P is true. If P is true, not P is false, right?
What do you mean by that?
So here, if the truth value for P is false, then if I negate that, then it becomes a true statement.
It's just gonna be all opposite.
Yeah.
Or P false.
So for as an example, Uh, 3, if P is 3 is an even number. That's false. Right? What if I negate this? Not P is 3 is not an even number. That's true. Right? So it just flips the truth value the opposite direction.
Inverse P is an even number. How's that work?
So the negation, we have to use a not in there.
So it's expressing the same thing as the other one, but it's.
Well, this is a false statement. Right, and then when I negate it, it turns it into a true statement. I use the false to true because it's the harder version, right? Where we go from a false statement, and then if I negate it, it makes it true. Right? The sky is green is false. Sky is not green. It's true. Right? So, yeah, the negation. But for us, we're just going to be working with the truth table mostly. We are going to be linking some sentences to their propositions and kind of slicing and dicing them that way, and that is difficult. But I'm going to hinge a lot of it on the truth table, and in that sense, it just flips the truth value, right? So.
I'm not gonna split. No.
Oh, okay. Well, this one would actually be quite difficult to negate. We're not even going to try it because it's a conditional statement. I should have had a divisor or something here. But so here's some propositions. I'm going to quit if I don't get a raise. Okay. This is what we call a conditional statement. And so here, these are conditional statements. And they probably should have been on the next page, but I didn't want to waste paper, I guess. Make more sense on the next page. So I'm going to quit if I don't get a raise. So here I've got the if. If I pass the final, then I'll graduate. I'll be going to the movies provided that my car starts. Yeah. So the middle one is already in a if some condition, then some conclusion. So if I pass the final, then I'll graduate. That's already in the if then form. But what if we take this little guy, I'm going to put it on the next page. You could rewrite this in the if then statement, right? So if I don't get a raise, then I am going to quit.
It's just a formal way to statement if go first.
Yeah. Yeah, so we use a lot of different variations of it in kind of our speech, but when we're attaching truth values to it, we need it to be in the if some condition, then the conclusion type of format. So what about the, bless you? What about the last one? Because the middle one is already in the right format. Yep. How about if my car starts? I'm just gonna cut some words. As long as you don't change the meaning, it's okay. And some of these, I will say the wording gets clunky, and you can just keep all the words if you want to, right? I don't mind. But I'm gonna shortcut this one a little bit. If my car starts, then I'm going to the movies. Then, although I think it's funny to say, I'll be going to the movies. So the reason being able to rearrange it in the if then format is because the conditional statement is going to be read as if P then Q. Okay? And the reason it's so important is because we're going to see that if Q then P does not mean the same thing, right? Logically, it doesn't mean the same thing. And so that's important. And so that's why we need to have it in the format of if P, then Q. We're going to denote it by a little arrow, right? So when you see this, if P, then Q is how you're going to read this. Okay, so I think it's worthwhile just giving you the truth table, and I want to highlight the one that throws people off. And maybe there's two, I guess. Let's talk about the general setup first, though. P0011, Q0101. We've seen that before, right? That's the same setup that we've seen already. But now the truth values for if P, then Q is going to be, so if P is false, then the condition is also, or the conclusion is also false, then the conditional statement is going to be true. And I've got an example of a teacher who makes a promise, and there are 4 different scenarios, right? 4 different scenarios. So we'll talk through those and kind of highlight why they're why it behaves in kind of a strange way. So I find that these two throw people off. So if the first statement is false, but then it's followed by a true condition, then the overall statement is true. Okay? If the first statement is true and the condition or the conclusion is false, then the overall conditional statement is false. Okay? And then if both of them are true, then the conditional statement is true. Okay?
Whatever if value overpowers Q value.
So the only time that it's false, right, is going to be this situation. Right. The only time where if P then Q is false is if we start with a true statement and then go to a false statement.
Yeah. How do the 2 falses make a positive?
Well, I've got an example. Might help. But this is the only false conditional. Okay. Because this one's tricky, and ultimately it's a matter of memorizing which one is which, right? Understanding it helps, obviously, but sometimes you have to start with memorization and go from there. But here is the scenario. So assume your instructor told you, if you receive a grade of 95 or better on the final exam, then you will receive an A in this course. That's, let's say, it's not a promise that I'm giving you, but I feel like if you get 95% on the final exam, you probably will get an A in this course, but I'm not making that promise. But let's say I did, right? Although I feel like I could, but I won't. Keep you on your toes. I go out, I make a statement, and I say, if you get 95 or better, I'm assuming percent, but it doesn't say, on the final exam, you will get an A in this course. Yeah? And so let's snag these little guys. Because I want to link the two. If P, then Q. What's our P in this case? P is that you got a 95 or better on the final exam. Right. Pardon? I'll say 95 plus on final exam. That's going to be our P. Our Q, then you will receive an A in this course. Q is you will get an A in this course. So if you meet the condition, then you will get an A. Okay? And so what the truth table is really saying is, okay, well, is the overall statement, so is the instructor telling the truth or not, right? If the instructor is telling the truth, then it would get a 1. And if the instructor is lying, then you get a 0, right? In terms of your truth value, right? And so what's the scenario here? If P is 0, so P is false, then you did not get 95 or better on the final exam, right? But you also didn't get an A in the course because Q is also 0, right? And so here, let's call this case 1, because I suspect I'm going to need a lot of room. Less than 95 and not an A. I'm trying to be kind of as shorthandy as I can. Okay? Because P is false, Q is false, right? The combination statement. You didn't get an A, but you also didn't get more than 95 on the final exam. And so the instructor is still telling the truth, right? And so that's why the overall truth value of if P then Q is true. The instructor told the truth, which means that P then Q is going to be a 1. If you don't meet the condition, then it doesn't matter. The overall statement is still true. Okay, do I use a different color? No, I'll run out of colors. The second scenario, you didn't, so if P is false, you didn't get 95 or higher on the final, or yeah, on the final exam, right? So less than 95, but you got an A in the course, that can happen, right? Maybe your grade going into the final exam was high, right? You just didn't do that great on the final exam. So less than 95, but got an A. The instructor still told the truth, right? You just didn't meet that initial condition, but that's okay because you still got an A, and so they're kind of off the hook. Feels good. Instructor told the truth. Because as long as the instructor is not lying, it's true.
She said,
But they got less than 95. But they still got an A.
but it says if you receive a grade of 95, you'll get an A.
What she
What
means,
is-
I think what she means is that, it's still possible to get an A grade if you're under 95, just that if you get a grade over 95, you're guaranteed to get an A.
Yes. Good. So it's, yeah, so it's different because this one, even though you got less than 95, if you had really high grades going into the final exam, even if you got less than 95, you could still get an A overall. So that's possible, right? But in terms of the instructor telling the truth or lying, the instructor wasn't lying. It's just that this statement doesn't really apply, right? And so from the instructor standpoint, they're still telling the truth, right? And that's what's so tricky about it. Let's see this one, because this is kind of the highlighting concept. I'll do it in pink to match because I copied and pasted it with pink. Case 3. Now P is true, which means you did get a 95 or better on the final exam, right? But if Q is false, then you didn't get an A in the course. And that's when you guys would come running to me and say, but you said you lied, right? And so that's why the truth value is 0, because in that scenario, yes, I would have lied. I'd fix it, obviously, but that's me personally. So case 3, you got 90, better than 95, but not an A, which means the instructor lied. And that's why it's a 0. The last case, you got better than 95 and an A, which means that the instructor told the truth. So we're back to 1. Making this type of connection for me is I would say it's really difficult, right? So since we're just starting, what I would say is if you're looking at a conditional statement, all you really need to remember is that it's only false if you start off with a false or a true statement and go to a false statement, right? This is the only time that you get a false overall conditional statement, right? And so that's where we can kind of start our memorization, because it's not better than that. So, but it's nice because there's only one scenario where it can be false, and then all the other ones are trues, right? But any questions on that one before we keep going? No. Yeah. So could probably use a little look over. There's something called the converse. The converse, which we also use in kind of regular language, right? You introduce something, you say something, and then you say conversely, right? Which means what? Which means the other way, right? So that's what the converse is. So the converse of a proposition, if P then Q, is this proposition, if Q then P. And that's why, again, it's so important that you're able to rearrange a statement into a if then statement, because that's the only way that you'll be able to identify the correct P, Q, right? And then when you write the converse, then you rearrange it, if Q, then P. So let's do the converse of the previous proposition. P was what? Let's see here. If you receive a grade of 95 or better in the final exam, then you will receive an A in this course. So then Q is if you get an A in this course, then you got a grade of 95 or better on the final exam. I'm just going to copy this. Whoops, I need more. I need more. Actually, let me use this here. I was pretty stingy with the space, I guess. So if Q, then P. Would be if you receive, let me bump this up here. If you receive, which I'm gonna have to see how to spell because I just kind of like run them together and make my eyes look like E's and my E's look like I's. If you receive an A in this course, then you got a grade of 95 or better on the final exam. Notice how that's not the same statement, right? Logically, they have different meanings. Okay. And so if you receive an A in this course, then you got a grade of 95 or better on the final exam. But we already discussed it, right? There is a way to get an A in a course without getting 95 or better on the final exam, right? And so logically, they're not the same, they're not equivalent, right? And so here, notice that if P then Q is not logically equivalent to if Q then P. And I snuck it in here. There is a proposition that's related to if P then Q that does have the same logical meaning, and that's the contrapositive. Yeah. And so the converse does not have the same logical meaning, but the contrapositive does. Now the contrapositive, I'll highlight it all, I guess, of if P then Q is the proposition if not Q, then not P. Yeah. Kind of combining our negations and our conditional statements. Yeah. And we'll show in a little bit that they are the same. Yeah. What we're going to find when we talk about logical proofs, probably not in this course so much, but in the next course that you have to take that I forget the number of right now, 251, I think. Is it 251? Anyways, then you'll rely on this quite a bit. Okay. And so the reason is that if you can prove the contrapositive, which is usually easier than proving the conditional statement, just the raw conditional statement, if you're able to prove the contrapositive because they're equivalent, then you've also proven the conditional proposition. Okay, so it's just kind of an easier way of proving things later on. Yeah. But for us, we're going to keep it up here. There's a third variation of this if P then Q, okay, which is the inverse. And the inverse has the same logical meaning as the converse. So the inverse and the converse are logically the same. And the contrapositive and the conditional statement are logically the same. Right? But what is the logical inverse? The logical inverse is of if P then Q is if not P then not Q. Okay, so that's the logical inverse. Okay. For example, if it snows today, then we have the day off. Wouldn't that be nice? Snow days. I'm not going to jinx it. Bless you. In terms of our P's and Q's, right? So now we need to link this statement up with P's and Q's, and that's where the order is important, right? So if P, then Q. So if it snows today is going to be our P. Then we have the day off, which will be my Q. So if I'm going to write if not P, then not Q, what does that look like? So not P, then not Q. If it doesn't snow today, if it doesn't snow today, then we will not have the day off. And those are logically equivalent. Any questions about those? Ready for more? How about the biconditional proposition? Bi means two, conditional, we've seen the conditional, so now it's going to be going in both directions. Okay, so if P and Q are propositions, then the biconditional statement, P if and only if Q, okay, meaning it's going to go back and forth, right? Has to go in both directions, denoted by this double arrow, right? So this is a biconditional statement. And we're going to read this as if and only if. Oops. Oops. Okay, I did do that on purpose, I guess. Sloppy. If and only if is usually abbreviated IFF. Only if. All right. The truth table for if and only if, while you have it. I actually forgot that I meant to take out the truth values so that we could build it together. Oh well. You win some, you lose some.
What's yours?
Pretty much.
Is that how it works?
Yeah. Yeah, some of them, I mean, you can do examples and stuff, but it is really hard to link the words to the truth values. So it's easier to memorize, sadly. I know, memorization, bad. Or is it? It's a muscle. Gotta work it. Okay. The biconditional statement, right, is the conditional statement, but it has to be in both directions, right? And so looking at this, right, it's pretty obvious what has to happen, right? 0 going to 0 and then 0 going to 0, both ways that's a 1, right? We think about, let me snag that, this little guy here. Copy. I'll put it beside here just so we can have a look. If you're going to a false, or from a false to a false statement, then it's true. Okay? And so then even if I move in the other direction, it's still true, right? And so that's why there's a 1 here, right? Because you're going back and forth between two false statements. There's no harm there. Okay? Now, we know if P then Q from 0 to 1, we know that's true right here. But then when I flip it and reverse it, then I'm going from a true to a false, which is false, right? And so that's this scenario here, from a true to a false, but up here because I'm moving in the reverse, right? And so now overall that's going to be false. Okay. This one, even moving in the P to Q direction is false. And so it doesn't really matter what the Q to P direction looks like, but it's going to be true. But we have a false already, so overall it's false. Right? Has to be true in both directions in order to be true. So I'll do recall this, but also must be true in both directions to be true. If I go from a 1 to a 1, then I go from a 1 to a 1, well, overall, that's a 1. Right? The biconditional statement is easier. Why? Because we see that, okay, I have to be moving from a 0, 0 or a 1, 1 in order for it to be true overall. Right? So here, note that if and only if Q is true, or is only true maybe, when P and Q have the same truth values. Just highlight those. Any questions about biconditional? So some things to look out for. All of these kind of phrases are equivalent to if P then Q. So P implies Q is usually kind of what I default to saying. Q follows from P. You could rearrange that as if P then Q. Right? P only if Q. Question? Well, sorry. Oh, this one is if and only if, whereas this one is if P then Q, and this is P if and only if Q. And I only have this bullet because otherwise I made the spacing all weird. So you can ignore that. But just some kind of phrases to look out for. I think the least obvious would be P is sufficient for Q and Q is necessary for P. Those are not, when I read those, it's not obvious to me that I can rephrase it as if P then Q. Okay, but you can because it's on here. All right. So the if and only if P is necessary and sufficient for Q, right? Has to go back and forth. P is equivalent to Q. If P then Q and if Q then P. I think that's probably the easiest way to think about the if and only if, the biconditional. If P then Q and conversely, so moving the other way as well. Okay. Let's do this first one together. I'm going to add a page here.
It's just you will need that.
Yeah, so we can negate bigger statements, right? But negation is just the opposite truth value of whatever you had. So you don't really need a truth table for it. I'll do. Some solutions, and maybe lines on the page would be nice, but I don't know how. Can never remember how. Okay, that's okay. If we let D be I-like discrete structures, and C be I will pass this course, and S be I will do my assignments, then we're going to express each of the following propositions in symbolic form. Yeah. And so I like discrete structures and I will pass this course. Kind of nice and easy, nice. So here, let me see here. I like discrete structures. I will pass this course and I will do my assignments. I'll do in green. I like discrete structures is D. And I will pass this course, which is C. I will do my assignments, or I will not pass this course. I will do my assignments is just S, or is that B? I will not pass this course. I will not pass this course is the negation of C. And if you prefer, you could wrap these up in brackets to indicate that, okay, that negation is only on C. It's obvious from how we wrote it, but we'll see kind of bigger statements where maybe you'll want to use some brackets to tidy things up.
Do you want us to use that one, or do you want us to use?
You can use a tilde or the logical not. That's fine. So this is the logical not, and the tilde is fine too. I'll know. Yeah. Okay. I think this next one is pretty sneaky. Why? It is not true that I both like discrete structures and I will do my assignments. Uh-oh. Okay. What's not true? This whole thing is not true. That I both like discrete structures and I will do my assignments. Right, so the negation is on the entire and structure. So D and S, but it's negated, right? That's sneaky, I think. So we start with, I'm going to start with D and S. But then we have to negate it. Because the whole both statement is the part that's not true. Yeah. I will not do my assignment and I will not pass this course. Okay. I will not do my assignment. I'll do it down below. Not S. And I will not pass this course. Not C. You can put brackets around this, these two individually, but you don't want to put brackets anywhere else. One thing that we will see much later is note. Logically, I can't just bring the negation inside. Okay? And so here, not D and S is not equivalent to not D and not S. In fact, if you wanted to distribute that negation, it would turn the and into an or by De Morgan's laws. But that's okay for now. I see I put a little Irish on there. There. Okay, fine, you got me. By De Morgan's laws, not D and S is equivalent to not D or not S. So the highlight would be on the or. Yeah, a later section, but yeah. I'm sneaking it in there. Little sneak preview. Just so that you're very careful about that. Now, what is up? Oh boy. Okay. I'll leave those for you to work on, try them on your own. But I will keep moving through because I want to work some more with some truth tables because that's important. I've posted an old version of the solutions. I'll kind of spruce those up and include them in the notes before I post them. So you'll have them. Logic is one of those, well, like a lot of things in this course, kind of up to you to practice it. It's really hard for me to show you every single scenario. I try, but it's hard. So what if we have a compound proposition such as, let's call it C, P and Q, or not Q and R? We could have broken down a compound statement and written it like this as C. So now we have propositions P, Q, and R, right? So now I have three propositions. Okay. Oh, here it is. So since each of the three simple propositions has two possible truth values, then that means that we have 8, right? 2 to the power of 3 different combinations. And so we're going to build the truth table for C, and 2 to the power of 3 equals 8. I'll sneak that in there. Knowing that you have 8 possible combinations, right? Maybe you need a little bit more room. I didn't give it to you. So just make sure that you can sneak in the header and 8 lines below it, right? And we're going to make a table. So it's going to look something like P, Q, R. I need to have all the possible outcomes and combinations of P, Q, and R. Draw a line across here. Bink. All right. If I have 8 total combinations, where do I start? Remember, for P, I start with all zeros, and I do half zeros, half ones. Right? So let's start there. 1, 2, 3, 4. 1, 2, 3, 4. Making sure that you give yourself enough space for 8 rows. This is just setting up the truth table, and then we'll build it out. Yeah. Okay, what do we do for Q? Now I take these zeros and I split them in half and do 0, 0, 1, 1, 0, 0, 1, 1. Right? Okay, 0, 0, 1, 1, 0, 0, 1, 1. And then I do the same thing for R, which now becomes alternating, right? 0, 1, 0, 1, 0, 1, 0, 1. Okay. So this is how any truth table with 3 propositions, this is what it's going to start out looking like, right? And so getting used to making this truth table, because on the test, there's more fun questions to ask with 3 propositions than 2 propositions, right? But the rules all stay the same. Okay, so what am I going to do? If I want to build out this compound proposition, what I'm going to do is I'm going to build little pieces of it until I have enough to put together simply. Okay? So for me, I start out and let's make a column of P and Q, right? We can do that. Can figure out the truth value of those. Then what would I do? I'd probably I'd make a not Q column, right? Negate Q. Or if you can do it in your head, but it gets kind of boggy if I don't have the not Q column made already, but then you want to have not Q and R. So let's do this. I'll do this in orange, and then I'll do the not Q in green, and then I'll do, not Q and R in blue. Try to keep it. And then overall, right? Because then what will I have kind of mushed up here? I'll have one truth column or another truth column, right? Which I can easily just make one, right, by the OR function. So here we go. Nothing to it but to do it. P and Q. P and Q, and this is where I would use my fingers and just kind of go down the line, right? I can't do that on here, but P and Q is only true if both of them are 1, right? And so the first one is 0, 0, 0, 0, 0, 0, cha-ching, cha-ching. Not too bad. We're doing it. Truth tables. We can do not Q. Not Q. I look at Q and I turn it the opposite. 1, 1, 1, 1, 0, 0, 1, 1, 0, 0. This is where lined paper would really pay off, I think. Try to keep them somewhat straight. Now that I have the not Q, which is optional, you don't have to. In fact, all of these kind of middle steps are not technically part of the truth table. I do expect to see them in your work, right? Because you can't possibly go from this to this overall statement. There's just no way. But if you're comfortable skipping the not Q, which I'm not, then go for it. But why did I need the not Q? Because I need a not Q and R. Not Q, and R. Okay. So here, not Q and R. It's only going to be true if they're both true. So I have 0, hey, 1, 0, 0, 0, 1, 0, 0. Now, C is really just orange or blue, or light blue, I should say. Right? And so now we just adjust where we're looking at, so orange or light blue. And I'm going to write it out properly, but C is P and Q or not Q and R. Okay. Or as long as one of them's a 1, it turns into a 1. Right? And so I have orange or light blue. Here we go. 0, 0 makes a 0, 0 or 1 makes a 1, 0 or 0 makes a 0, 0 or 0 makes a 0, 0 or 0 makes a 0, 0 or 1 makes a 1, 1 or 0 makes a 1, and 1 or 0 makes a 1 again. Did it lock? The subtle. You bet. There, we did it. That's the truth table for this compound statement. Right? How do we use it? We aren't going to use it for very much, but the only times where it's true, this overall statement is true, right, would be when we have ones here. So if we look at this first row, that's if, so it's only true when P is false, Q is false, R is true, right? That's one combination where this logical statement, this overall logical statement is true. Party time. Another option would be if P is true, Q is false, and R is true. That's another way that we could make this an overall true statement. So if you've studied philosophy, they do a ton of logic, right? Like a ton. It's not what I like. I love truth tables though, because you can just kind of pick your way through it. But linking this to a sentence, I don't like. And that's okay. Hey, here it is. This should have been at the very beginning. What was I thinking? If C is generated by n simple propositions, there it is, then the truth table for C will have 2 to the power of n rows, with the first n columns being an enumeration of the n-digit binary integers. Right? So here we've got 3-digit binary integers, but it does keep with the flow of 0, 1, 2, 3, 4, 5, 6, 7, 8. Or I guess 7. I did it again. When I was reading my notes, I had a boo emoji. Boo. I don't like this. And we don't really use it. I had to put it in there because it's the actual definition of propositions generated by a set, but we're not actually going to use it. Maybe I shouldn't have an old school emoji in there, but It's what I had in my notes. Let S be any set of propositions. Now, a set of propositions could be finite, like P, Q, R, like we saw, or technically it could be infinite, but a proposition generated by S is any valid combination of propositions, which we can make with conjunction, which was what? That was and, right? So conjunction, that's worth reviewing. And disjunction, which is or, and negation. What's interesting is we introduced a lot of other things, right? The conditional statement, for example, but we can build all those statements from just those three. So that's kind of cool. And so blah, 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 ignore that. I have it on there because we have to have it on there, but we're not going to use it. If S is a finite set, though, okay, then we're going to use slightly different terminology. So if we have S is a set of PQR like we had earlier, okay, then we might just say that this proposition is generated from PQ and R instead of from the set of PQ and R, just subtle differences. Okay? And what do we need? We saw earlier when we made that truth table, right? We need to have a way to figure out how can I break down this kind of bigger statement into smaller statements, right? Making sure that I'm kind of lumping them properly, right? Kind of like BEDMAS in a way, right? Brackets, exponents, division, multiplication, addition, subtraction. First thing you're going to do is the negation, which is, of course, the negation. Second thing you're going to do is the conjunction, so the and. Then you're going to do the disjunction, which is the or. Then you're going to do the conditional operation, which is the single arrow. And then you're going to do the biconditional, which is the double arrow, or the if and only if arrow. So we work from left to right, okay? And all of these are overridden by parentheses. So if you've got parentheses or brackets, then you override that order. But even within those brackets, you follow this order. Okay. And so by these rules, just as an example, P and Q or R, and comes before or, but also left to right. So either way, it would be P and Q first or R, right? If we broke this down. So these rules are used in computer languages, of course, to interpret logical expressions, right? On-off switches, that kind of thing. What if you have to use parentheses to clarify the order of the operations in this example? So we're just going to wrap things up in brackets and then build out, right, and start from the very middle of the parentheses. Remembering you're reading from left to right, and there are no brackets here, so there's no overriding it. Yeah. How about A? From left to right, I would have to do P and Q first. And R. Whoops, I threw in another bracket.
Would it work if you do Q and R first and then You have to.
No, it wouldn't. That's the sticky part. Yeah, so not like multiplication, I guess. How about not P or not R? First, you have to negate the P and separately negate the R and then do the and. Or sorry, or not P or not R. Throw those in brackets. Not P. Well, first I have to negate the P on the inside and then I can negate it on the outside.
Isn't that just conjunction? Or isn't it just P then?
Yes. It is. But it is because you've done it in this order. Right? Not P, and then negated it again, flipped it back. Oh, this last one. Okay. I'll just write it out plain, kind of bigger. P, if and only if Q and R, then S. So reading from left to right, I don't have any brackets to deal with, but I do know from my hierarchy, right, that, okay, first negation, there's no negation, right? Then conjunction, which means that I need to do Q and R first, right? And so first I need to do Q and R. Then the disjunction, but there is no disjunction. And so the next thing I'm going to do is I'm going to do the conditional. Q and R has now become one column in your truth table, right? So if that, then S. Right? And then I can treat that as one thing to go between P and this big blob.
Do you ever use curly bracket conjunctions?
Curly brackets? No. You can if you're running out of brackets, but I would prefer it if you use square brackets. If you wanted kind of overarching brackets like this. Just because the curly brackets now means sets to us, right? So set notation, but you can use square brackets if you want to have kind of bigger brackets. And I should have. So thank you. Okay. Let's make a truth table of one of these. Uh-oh. Let's see here.
For example, will you be giving us the truth table for each one, or are you just wanting us to memorize this?
You'll just have it in your brains. I know, right? Eek. This one I'm noticing doesn't have any conditionals. Which one of these should we do together? And then I'll post the solutions for the rest of them. I guess A makes the most sense. Although it's kind of easy. For A, I only have P and Q that I'm dealing with, right? So my original propositions are just P and Q. So then I need to have 2 to the power of 2 rows. So that's a good place to start. PQ. And same method as before, 0, 0, 1, 1. For Q, it's 0, 1, 0, 1. Now to make the truth table for not P and Q, but the P and Q are together. So I'm first going to find P and Q, and then I'm going to negate it. So P and Q, 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1. And then if I negate it, I just flip those. 0 becomes 1, 0 becomes 1, 0 becomes 1, 1 becomes 0. So I want you to practice those on your own, but I've got a better truth table for us. Any questions before we talk about equivalence? Okay. If we have 2 propositions R and S, then they're equivalent if and only if R going back and forth between S. Let's think about it that way. The biconditional between R and S. Hey, did I skip something? Hey, I did. Nice try, Emily. There's more stuff on page 5. Sorry about that. Like a tautology, of course. We haven't talked about tautologies. Here we go. So equivalence and implication by example. So I just want to kind of build it up. So I want you to compare the truth tables for not P and Q, which we just did conveniently. So maybe I'll snag that. And then not P or not Q. Now I already kind of gave you a heads up that these will be equivalent, logically equivalent, right? And now we'll see how that works. So let me just grab this work that we just did. So it's not for not. Copy. Put it in here. Make it way smaller. Oops. Okay. So we found this one earlier, and I'm just stealing it again. So now I want to make another truth table or another column of not P or not Q. And again, if your brain is kind of working in overdrive, you could probably do the not P in your head and the not Q in your head, but I can't. So for me, I need to make a column of not P, a column of not Q, and then I can build the next one. Yeah. But like I said, all those are kind of optional. But I encourage you to do it because what a mess if you don't. Flipping these, I get 1, 1, 0, 0, and not Q is 1, 0, 1, 0. And then if I do not P or not Q, then that's these last 2 columns that I just made. 1, 1 in there, at least 1, 1, it becomes 1. And so I get 1, 1, 1, 0. Notice that these have the same truth values. Yeah. So in all four cases, right, regardless of what the setup of P and Q are, right, they're going to have the same truth value, or not regardless, but for the same combinations, they have the same truth values. Okay. And when we use the biconditional operator, then remember the biconditional, the if and only if moving back and forth is only true if I've moved between the two of the same truth values, right? If I'm going from a 1 to a 1 and backwards, that's true. Or if I go from a 0 to a 0 or backwards, that's true. The other two are false, right? And so then if I do this, if I have not P and Q, and I do the biconditional of not P or not Q, what do I get? Right, the biconditional is only true if I'm moving from a 1 to a 1 and backward again, or a 0 to a 0 or back again, right? But because these are the same, right, then I am bouncing back and forth between the same values for each of these rows. And so what I get here is 1, 1, 1, 1. So the result is a value of true in all cases. Yeah. And this is what we call a tautology, which I tried to just incorporate on the next page, I guess, but that's when I realized I had skipped some stuff. Yeah. So this is called a tautology when you've generated just all the combinations of P and Q for this statement. They're all true. Yeah. Now, I'm concerned about the time, but I do like to ask these questions where I say use a truth table to confirm that each of the following are tautologies, because then you know what you're working towards, right? And you can kind of confirm that they are tautologies. I'm telling you that they are all tautologies. So you can work on building those tables out. We already did the first one. Right. So this one we did. But you can try the other two on your own and confirm that they're tautologies. Right. On the flip side, a contradiction is an expression where all the logical values are false for all the cases. So you get, instead of all ones, you get all zeros. Okay? And so again, we could use a truth table to confirm that each of these are contradictions. Right? But I want to talk about equivalence, right? We've mentioned it, logically equivalent. And so what we have is if I have two propositions R and S, they're equivalent if and only if the biconditional statement is a tautology. Okay? And so if the biconditional is a tautology, then we double up on the double arrow and we say that they're equivalent to each other. So the equivalents R and S are equivalent if and only if the biconditional yields a tautology. And then we introduce this new notation, the double arrow. That means that all tautologies are equivalent to each other, right? Because moving back and forth between tautologies, I get the same thing. I get all ones, I get a tautology again. And all contradictions are also equivalent to each other, right? Logically equivalent. And so here, note all tautologies are equivalent to each other. And all contradictions are equivalent to each other.
It just have the extra line for biconditional.
Yes, if the biconditional is a tautology, then they're equivalent. The implication is essentially the same, but for the conditional statement, so it only has to move one way. And so we say that R implies S if R then S is a tautology. Yeah. So then we write that R double conditional arrow to indicate the implication, which would be different from equivalence, right? Equivalence has to move back and forth, but the implication only has to move in the one direction, the conditional. Disjunctive addition is not something that I'm going to have you know. How do I indicate that? I don't know. But I do want you to be able to use a truth table to show that this is true. So P implies P or Q. And so what do we have to do in order to prove that this is true? Then you have to know that, okay, when I make this truth table with just P, if P then P or Q, I have to get a tautology, and then I've shown that P implies P or Q. Whew. So that's how it's going to go. Let's do it. P, Q, those are the only propositions I'm dealing with. So I'm gonna have a little table here. 0, 0, 1, 1. 0, 1, 0, 1. I need P or Q. 0, 1, 1, 1. And then I need a column of if P, then P or Q. Remembering what? The only time that this conditional operator is false is when I go from a true to a false, right? All the other ones are true. So from a 0 to a 0, now notice, so from P going to P or Q, so I'm going from the far left to this newest column, right? If 0, then 0, that makes a 1. If 0, then 1, that's a 1. If 1, then 1, that's a 1. And if 1, then 1, that's a 1. This is a tautology. Therefore, P implies P or Q. And so that's how you're going to show that. I need some way to indicate that I'm not gonna test you on a concept. How about if I underline it in red? It means I'm not gonna test you on disjunctive addition. Only what we just did, right? Being able to show that a conditional is a tautology, and that means it's an implication. And the Sheffer stroke, I just had to include it here. Even the textbook doesn't talk about what it does or anything. Just says, here's the truth table for it. Go ahead. It's only false if they're both ones. So that's weird. Okay. And because I'm out of time, on the last page, you have some laws. We've already seen De Morgan's laws. We saw these earlier, not because you wanted to, but because I snuck them in. Okay. And there's also names attached to some common implications and equivalences, right? More for if you're going into law or philosophy, then that would be useful. But that's it for me. If you have any questions, let me know. I'll fill in the rest of the solutions and then I'll post the notes. How about that? And I will not see you on Friday. You'll see me in a video. And I hope you enjoy your long weekend.